A confirmation from anyone?
Yes, sir.
Yeah, so do that quickly because so every second counts, right? Okay, now let us try to um, now that you became better prepared after your test, now know all the things that we have covered so far, right? So you know much better than before. So let us try to understand little bit about something called the local area network. So local area network we have already understood, right? And Ethernet is a very popular protocol which is used for running the local area networks. So in one of the introductory classes, we have seen that there is local area network, there is wide area network, right? And local area network is basically limited geographically, right? So a department of an institute may run a local area network, or a campus, entire campus may run a local area network, or sometimes it can be restricted to a building. So basically so local area networks have restricted geographical area, right? It's not very big in size. Okay, so local, it's a local area, right? So that is why it's called local area. Achha, by the way, has the recording been started? Let me just check. Okay, that's fine. Okay. Okay. Now, yeah, so local area networks can be like standalone. So where you have number of different isolated computers, standalone computers forming an isolated network, right? Um, and it could be belonging to a particular organization or a particular department. You can have so a local area network which doesn't go anywhere outside. It is not visible outside a particular organization, or you could so you could have you could have it connected to the internet, or the wide area network, right? So most of the local area networks nowadays are actually connected to the internet or the wide area network, right? um, so this local area network actually became very popular in the 1980s and so on, right? So after 1980s, basically after 1980s, local area networks became very popular, and so local area networks like not only the Ethernet, but also there was something called the token ring, token bus. There was a local area network using FDDI, using fibers basically, right? Fiber distribution interface, FDDI. And so all of these, like so these became very popular. um, However, they were restricted in terms of how much performance they could offer, right? So the data rate, for example, packet drops, etc. So these kind of restrictions were there with respect to these different parameters. Now, later on, actually, there was another technology which is kind of obsolete now, a high-speed WAN technology, which is called ATM, right? So ATM, not your ATM machine from where you withdraw money, but there was an ATM technology for having ATM communication technology, basically for having high speed WAN connectivity, right? So that became very popular. Now ATM was primarily intended for having high speed WAN. However, the concepts of ATM were borrowed to form the ATM LAN, right? So basically, the similar kind of things that were there for the WAN to offer high-speed connectivity. Those concepts were borrowed and was embedded to the LAN technology to form the ATM LAN. However, ATM became eventually kind of obsolete, and people do not talk about ATM LAN or ATM WAN that much anymore. So Ethernet is basically the only LAN technology out of these which still has remained popular, right? And it has grown to be very popular. Okay. So Ethernet, the success for Ethernet is due to number of reasons, right? Due to the way Ethernet was designed, right? So the way Ethernet was designed, basically, so the way, so in the modular way, the Ethernet was designed so that it can offer higher transmission rates. And so higher transmission rate, etc., higher data rate, it can be offered with Ethernet. And also Ethernet, so it is a technology which is scalable, and I will show you how it is scalable. So the advantage is that you can grow the Ethernet using Ethernet. Basically, you can grow your network without losing too much of performance. Okay. When I say performance, it is basically the network performance. And when I say network performance, typically the network performance parameters are like, how much is the delay, end-to-end delay, how much is the throughput of the network. That means how much, how many bits can be transmitted per unit time. Then there is something called the jitter, which is actually the delay variation with respect to time and so on. So anyways, so Ethernet basically stood the test of time, right? So Ethernet is still popular. Ethernet has been popular, and so that is why actually we need to understand that what are some of the important concepts in Ethernet, right? So that is what we have targeted in this particular lecture. So let us go back and try to understand um, a very popular project that was started by the IEEE Computer Society in 1985, right? It was called the Project 802. Now this 802 project basically led to number of different standards. Okay. So 802 basically led to the evolution of a set of standards. These standards were intended to enable the interconnection between different computers and other devices in the network, right? So basically the whole idea of project 802 was to basically integrate with the existing TCP IP protocol suite or the OSI model, which we covered yesterday, without actually replacing any of the existing vendor equipments. Okay. So this 802 project, it mainly looked into specifying the functions of the physical layer and the data link layer of major LAN protocols such as the Ethernet. So Ethernet also belongs to this 802 family of standards. There are many other standards which belong to, sorry, there are many other technologies that belong to the 802 family of standards. Wi-Fi is another one. There are many other ones which I am also going to show you shortly. So the whole focus of 802 was on the physical layer and the data link layer, providing the specifications about these two different layers, right? So whether it is Ethernet, whether it is token ring, whether it is token bus, whether it is FDDI. So for each of these different major transmission technologies, basically this 802 project, it offered different specifications for the physical layer and the data link layer. Okay. Now, when I say data link layer, we will see shortly that the data link layer, we have already actually when I covered data link layer previously, I already mentioned it, but we will look into it in more detail in the context of Ethernet, that this data link layer has two major components, two major parts based on the functionalities. One is called the LLC, logical link control. The other one is called the medium access control. So in the context of Ethernet, we will look at both the LLC and the MAC. Okay, so our focus in this particular lecture is going to be on the specifications for the physical layer and the data link layer for the Ethernet. So this physical layer, we have already visited physical layer yesterday, and so it is dependent on the implementation and the type of the physical medium that is in use, and the different types of transmission medium we have already covered in a previous lecture, where we have seen that there are guided, unguided media which could be used. That so basically the protocols that you are going to use in the physical layer depends on the type of transmission medium that you are trying to use. Okay, so IEEE basically gives you a set of protocols that you can use in the physical layer in order to implement the local area network. Okay, so so we will look into this thing in more detail. Okay. Now, apart from physical layer, on top of physical layer, in fact, we have the data link layer, as we saw in the previous figure. So the data link layer basically is primarily concerned about two things. One is how to do logical link control, LLC, which basically includes issues such as flow control, error control, framing, and so on and so forth. These are all part of the logical link control. And when we talked about data link control in a previous lecture, we have seen the different mechanisms of how to handle flow control, error control, framing, etc. Apart from this, we also went through in the generic way, not in the context of Ethernet though, how to do medium access control when we were talking about these multiple access control protocols. Okay, so medium access control actually talks about that how the different stations, how the different computers who are accessing the shared medium, what discipline you are going to enforce in order for them to be able to get access to the medium. And the third thing is the framing, and framing basically, here we are talking about that how you can take these bits and put them into encapsulated units which are called the frames. So how you can build these frames is what concerns framing. So there are different components of a frame, right? So if you are talking about a typical frame, right? So if you are talking about a typical frame, it has an address, it has a control component, and it has the data field which holds the data that actually has to be transmitted, and then it also has something called the FCS. The FCS is basically the acronym for frame check sequence, right? Now this kind of frame, okay, so this kind of frame, so it has, again, it can be divided into either the LLC PDU or the MAC PDU, MAC frame basically, right? So there are two different components. So each of these are shown over here, but so I'm not going to go through these in further detail, but basically, so maybe, so I will touch upon little bit some of these different terms that you see over here, but for now actually it is sufficient to understand that the data link layer is primarily concerned with three things: logical link control, medium access control, and framing, right? So let us go ahead and try to understand a little bit more about the other details that are required to understand Ethernet. Now, so we are in this lecture, our focus is on this small area network within a building, within a campus, within a department, which is called the local area network, right? So this local area network serves as a broadcast domain. Okay. So what is a broadcast domain? A broadcast domain is basically a logical connection of different computers that basically receive, or it has the potential to receive, a broadcast traffic that is sent from any of the other computers. So that's the broadcast domain. So it's basically a logical division, as I said, and when there is a broadcast that is made in a broadcast domain, all the other computers which are part of that domain can hear the broadcast through all their interfaces. So this broadcast domain concept is important because LAN basically helps you to create a broadcast domain. Okay, it helps you to create the broadcast domain. Now this is important because so when you are talking about broadcasting, so in the data link layer, broadcasting is important because some of these different stations which are shared wired or wirelessly, they can hear all these broadcasts of the data frames that are transmitted between the different nodes. So you do not really have to take help of any fancy network technology devices. So broadcasting with the help of these broadcast frames, basically, so all the stations very efficiently they can hear the transmission that is going on through all their different interfaces. So this broadcast domain is basically restricted to anything in between the domain of the router or the the higher layer devices, right. So basically, a broadcast domain, at the periphery of the broadcast domain would be basically these routers. So routers are not going to allow you to send the traffic through when you are talking about broadcast domain in the context of LANs. Okay. So basically LAN basically can help you to create this broadcast domain. LAN is a broadcast domain basically, right. So here each of the receiving nodes, it will check the destination address of a particular frame. So whenever a frame is received, the node basically which receives the frame, it is going to check the destination address of that frame, and it will simply ignore any frame that is not addressed to its own MAC address or the broadcast address. Okay. So that is the whole idea, right. So with this idea, this broadcast domain basically functions. It is also possible that not all computers in the broadcast domain are basically directly connected to each other. Some of these could be bridged. So basically, you can have the computers to be part of the same LAN segment, or you can have multiple LAN segments to be bridged with each other in the broadcast domain. Okay. So that's the whole idea. Now let us come back to the Ethernet, how it evolved. So Ethernet it evolved right from the 1970s. Okay. So in the 1970s, basically, Metcalfe and Boggs, basically they came up with the Ethernet, use of Ethernet for forming the local area network. Okay. So since then, basically Ethernet has gone through different generations, right. It started, the standard Ethernet is the one which was initially started, and so standard Ethernet was there. Standard Ethernet offers a data rate of 10 Mbps, a speed of 10 Mbps. Then evolved the fast Ethernet, which offers a data rate of 100 Mbps. Then came the gigabit Ethernet, which offered 1 Gbps of data. So when I was a student, basically this gigabit Ethernet was popular, right. It was a new technology those times, right. And then you have the most evolved version of the Ethernet, which is called the 10 GB Ethernet, which is basically 10 Gbps data rate, right, 10 gigabit Ethernet, right. So you have these 4 stages of Ethernet evolution. However, keep in mind that most of the time we are going to discuss about the standard Ethernet, which is the 10 Mbps Ethernet. So we will understand generation after generation how this Ethernet evolved, with more focus on the standard Ethernet. Now let us start with the standard Ethernet. So what did I say? That Ethernet basically gives the specification for the physical layer and the data link layer, right. Now in the data link layer, basically Ethernet uses the one persistent CSMA CD. Okay, and now that you have appeared for the test today, can you tell me like what is the one persistent protocol? What is one persistent? Who can tell? What is the one persistent protocol? Today only, just only an hour back you appeared for the test. What is one persistent?
Sir, it keeps on listening. If it finds idle, the station just sends the frame with
Then
probability
what?
1.
Yes. Okay, it will send with a probability 1, right? If it if it finds. So now what is the problem with one persistent protocol? What is the disadvantage of the one persistent protocol? It is very, I mean, the advantage is that it is very simple, right? It is very simple to implement, right? And basically the standard Ethernet used to use this one persistent protocol. But what is the disadvantage of the one persistent protocol?
Multiple stations may initiate a frame if they find.
Exactly. So that would lead to a collision, right? And that eventually is going to lead to lower data rates, right? Very good, very good. Now, so we will come back to this particular issue, but let us also try to understand that for the standard Ethernet, so it uses the concept of the slot time, right? The slot time is defined to be the round trip time plus the time required to send the jamming sequence, and this jamming sequence, etc. Earlier when we covered CSMA CD, you have already you already know about it, right? So this entire time, right, and why it is the round trip time, that also we have looked into previously, and plus adding the jamming sequence time, so these two basically together gives you the slot time in CSMA CD, sorry, in the standard Ethernet. Okay, so the round trip time basically is the time that is required for the frame to travel from one end to the other, right, in the maximum length network, right? And again, it is round trip time, right? So then getting the this thing back, right? So sending the data and sending the frame and the time required for it, and then getting the this thing back, plus the jamming sequence basically, right? So you together you add it and then you get the slot time, and it is the slot time that is important because it governs how much time basically the stations are going to get in the standard Ethernet to transmit. So now let us look into another thing, which is this logical link control, LLC, right? So this LLC basically it defines a programming interface between the part of the communication software that controls the network interface card, okay, and it creates a reliable data transfer mechanism at the data link layer, right? So this LLC basically is concerned about number of different things, including flow control, error control, and framing, right? So these things basically we have already gone through. Now, if you are talking about the 802.2 standard, right? It basically has different fields, right? It has different fields. So first one is the first part is the header, the LLC header, and the next part is the information. The information is actually where the data are stored. However, the header has three different subparts. One is the DSAP address, SAP address, and the control. Right. So what are these DSAP and SAP? So SAP stands for service access point, right? So SAP stands for service access point. Now this service access point, basically tells you like what is the network layer entity that has created the message. So when we are talking about SAP, basically we are talking about the source SAP, right, which is basically the 8-bit long field that represents the logical address of the network layer entity that has created the message, right? So it is, that is why it is called source SAP, right? Source service access point, it's basically the logical address of the network entity that created the message. And then you have the destination SAP, which basically is the same thing like before, but here it is actually the network layer entity which is intended to receive the message. Okay, so that support is basically offered by this particular LLC sublayer. Okay, so that's about this, and now let us try to have a look at the different 802 class of standards that have been proposed. So 802.1, so we are still talking about the project 802, right? So I told you earlier that project 802, it created different standards. So here are some of the standards that were created by project 802. So the first one is .1, 802.1, which basically provides the standard for bridging in the local area network. The logical link control is offered by the standard 802.2. Ethernet is .3. The specifications for Ethernet is .3. Specifications for token bus and token ring are .4 and .5 respectively. Wi-Fi that we all popularly use is also part of this 802 family of standards. It is actually 802.11. And then there are few others which you may not have heard about, but these are actually primarily used for forming different types of personal area networks. The first one is 802.15, 15 category. So this is basically for wireless personal area network, right? And then 15 basically has many different substandards, not substandards, but basically different other standards which are part of this 802.15 category. So the first one, .1, basically Bluetooth is part of the 802.15.1 standard, and ZigBee basically is part of this 802.15.4 standard. So part of means like these technologies basically follow these different standards in their specification. So if you are more interested to know about these standards, so I have also given you the reference from where you can get further details about these different standards. So let us first talk about, not first, let us focus on the 802.3 standard, which basically is used for the Ethernet, the standard Ethernet, right? So in the standard Ethernet, as I said, like there are different things. So one of which is basically the MAC sublayer. So the MAC sublayer basically governs the operation of the access method. So which of the stations in the shared medium is going to get access to the medium when, right? So basically this MAC sublayer basically governs this particular aspect. So it also, this 802.3, it also frames the data that is received from the upper layers and passes them to the physical layer, right? So if we look at these frames that are transmitted, right? So these frames that are received from the upper layers, the data that are received from the upper layers are framed in the data link layer, and then they are passed on to the physical layer. So how these frames are going to look like, right? So the different fields in these frames are shown in this particular picture. So we have the preamble, then we have the SFD. Okay, so SFD is basically the start frame delimiter, SFD, start frame delimiter. Then you have the destination address, source address, length or type, data and padding, and CRC, cyclic redundancy check, right? So these are the different fields of a frame. Strictly speaking, the first two, preamble and SFD, you cannot call them to be part of the this MAC sublayer, because these are actually part of the physical layer, right? So these are basically part of the physical layer, so you can think of them as physical layer headers, whereas the rest of the ones are basically part of this MAC sublayer. Now, So what are these different fields basically, right? So this preamble, so let us try to take one after the other. So this preamble basically gives you, it's basically a, it's a string. It's a string of alternating zeros and ones, right? It's a string of alternating zeros and ones that basically helps to alert the receiving system that whoever receives it, that sequence, by looking at that sequence, that system will think that a new frame is coming. Okay, it will think that a new frame is coming, and then that particular station which sees that particular preamble or this particular sequence, what it will do is it will synchronize its clock. If it is not synchronized, then it will synchronize the clock. So this particular pattern that is provided, okay, by this particular preamble, it it not only alerts about this particular thing that a synchronization is required, but also it also carries a timing pulse, right? It also has, inside it, it also has a timing pulse. This timing pulse basically can help in this particular synchronization aspect, right? In this particular synchronization aspect. Then comes the SFD, right? This SFD, as I said, is the start frame delimiter. So as this name suggests, right, this SFD basically tells the station which receives the frame that it has to finish any synchronization that it has not done yet. Okay, and then it also tells that the next field is going to be the destination address. You see that SFD, basically the next field is the destination address. So this is 1 byte long, right? This is 1 byte long, and it has a particular sequence. This SFD basically has a predefined sequence, and this, what is this sequence? It is 10 10 10. So 10 how many bits? 6 bits, and then you have 2 other bits to make it 8. The last 2 are basically 1 1. So 10 10 10 11. You see over here 10 10 10 11. So these two 11s are kept at the end intentionally to signify that immediately after these 2 bits, the field that is going to come is the destination address. Now this destination address, I do not need to tell you, right? It tells you what is the destination station which is supposed to receive the packet, right? Then comes the source address. So by the way, all these different fields, their corresponding length are also given over here. In the interest of time, I am not mentioning them, but it is visually understood, right? So destination address, for example, is 6 bytes. Now the next 6 bytes are going to be the source address. Okay. So you see that the issue of synchronization, the time synchronization that I was talking about, this is very crucial, because if there is little bit of synchronization gap that happens, everything is going to be misinterpreted, right? So this time synchronization is a very crucial step before actually these different fields can be deciphered. So this destination address, then comes the source address, another 6 bytes, then comes something called the length or the type. So this type basically is what? What is this type? This type or the length basically defines that what is the upper layer protocol, okay, whose data is basically encapsulated within this particular frame, right? What is the upper layer protocol? What is the upper layer protocol? This upper layer protocol, what is the upper layer above data link layer? What is the upper layer? Anybody? What is the upper layer? See, you all are not listening to me, and then later on, you will again land up in trouble. Probably, you all are doing something different now, right? So if you are not attentive, in the class, actually many things I tell you, if you do not listen, then later on, you will face difficulty. Okay, so anyways, so this upper layer protocol, I mean upper layer, what is the upper layer? Upper layer is basically the network layer, right? The same TCP/IP or the OSI stack. So this upper layer basically supports different protocols like IP, OSPF, RIP, ARP, and so on and so forth, right? So it tells, like, which protocol basically, which packet basically is encapsulated within, which protocol packet basically is encapsulated within the frame, right? So it tells you about that. Then comes the data, right? So this is this data part. Okay, so this data basically, data and padding is basically some extra bits are given for, again, helping. So let us not get into the padding, but basically this data basically has the upper layer data that is actually stored in them. And then finally you have the CRC field, which is the 4 bytes long field, right? So this particular field basically contains information that will be helpful for performing the CRC check that you learned when we covered error detection, right? So this CRC check for error detection during transmission can be performed with the help of the information that is stored over here in this field. So this CRC check is going to be done over the addresses, the types, and the data field. So if the receiver basically receives the CRC and then it finds after the check that it is not 0, right? Then it assumes that the data that it has received after the CRC check, it is not correct, right? It's corrupted. And if it finds that it is 0, then it accepts, otherwise it discards the frame. So this CRC check basically can help you to detect that the data that you have received, right, and the information that you have received is the correct one, right? So so that's the CRC field. Now comes the frame length, right? What is this frame length? See, Ethernet has basically imposed certain restrictions on how much long the frames are going to be, right? So the minimum length of the frame and the maximum length of the frame are basically imposed by Ethernet. So in Ethernet, in other words, Ethernet frames have, all Ethernet frames have a minimum frame length of 64 bytes or a maximum frame length, not or, and a maximum frame length of 1518 bytes. So the frame length is going to range from 64 bytes to 1518 bytes. Okay. So the different fields over here are shown over here. The data comes in over here, as we have seen before. Now this data basically ranges from the 46 bytes long to 1500 bytes long length, right? So data basically, the payload, actual payload basically ranges from 46 bytes to 1500 bytes in every frame, and together the minimum frame length is going to be 64 bytes and the maximum frame length is going to be 1518 bytes. Now, so far everything is fine. You have a frame. So these frames will have to be transmitted, right? So the data eventually will go through the physical layer, and the data link layers of the two computers that are exchanging the information, they will start talking to each other, right? Now the question is that the data link layer of source computer and the data link layer of the destination computer, how they are going to find each other. So for this, basically in the data link layer, an address is given which is called the physical address or the Ethernet address, and this Ethernet address is basically it's a 48 bits long address, right? It's a 48 bit long address. Okay. So this Ethernet address is 48 bits or 6 bytes, right? 48 bits or 6 bytes long, and basically it is written in hexadecimal notation, right? So so these are the 6 bytes, right? So 1, 2, 3, 4, 5 and 6 bytes, right? So each of these are basically hexadecimal numbers. Okay, so these hexadecimal bytes are basically hexadecimal numbers which are like 1 byte long. These are basically separated with a colon, right? And this is how basically the Ethernet address looks like. So if you are talking about a broadcast LAN, so this Ethernet address is sufficient to have the two computers to send or transmit the packets to each other. So addressing is definitely important. Yesterday also when I was talking about this OSI layers, etc., at that time I told you that addressing is important, because in every layer you need some mechanism for the entities to talk logically using this address. So in the data link layer you also need an address, and it is this Ethernet address basically also called the physical address, which can help you to talk to the corresponding peers in the corresponding the layers in the corresponding peers, right? The corresponding layers in the corresponding peers basically, right? So that means the data link to data link, basically that communication can take place with the help of this Ethernet address. Okay, now one more thing before we one more thing quickly before we close. So these addresses basically, these hexadecimal 6 bytes of hexadecimal notation addresses, basically these addresses basically can be classified into 3 types. One is the unicast, the second is the multicast, and the third one is the broadcast. Now the source address, it's always unicast, because it is from the source from where all the frames are going to be generated. So it is one station, so it is always the source address is unicast address, right? The destination address basically can be either unicast, or it can be multicast, or it can be broadcast, right? Now look at over here. So look at the first byte. If the least significant bit of the first byte in the destination address is 0, that means what is the least significant bit of this byte? This is the 1. This is the first byte, right? So if the least significant bit of the first byte is 0, then it is unicast address. Otherwise, it is multicast address. Clear? Okay. Now, so this is the unicast and the multicast, right? So broadcast addresses basically, broadcast addresses in so the these are basically special addresses where all the bits are going to be marked as 1. All the bits are going to be marked as 1, right? Not just the least significant bit, but all the bits are going to be marked as 1, right? So the broadcast destination address is a special case of the multicast address where all the bits are marked as 1. Okay. So whenever a station basically receives such a frame with all these ones marked, then it knows that basically it's a frame that is destined to be broadcasted. So it is going to broadcast, that particular station is going to broadcast through all its interfaces. Through all its interfaces it is going to broadcast. So today we do not have time. Next class onwards we'll talk about the different categories of standard Ethernet. Okay, so that we will defer for next class. Okay, so thank you. We are actually already past the time. So thank you so much.